Hello guys, my name is Faramaz Dolati Ardejani. Welcome to my channel. Today I am going to continue my lecture on groundwater flow equations. Let's take a look at this picture here. The water that is removed from the aquifer by pumping, or the water that enters the aquifer as a result of precipitation, are considered to be sink or source terms for the groundwater flow equation, which cause the Laplace's equation not to be established in all points inside the aquifer medium. In this case, Poisson equation is used instead of the Laplace's equations. This equation means the sum of the second partial derivative of hydraulic head with respect to x, y, and z plus q is equal to 0, or del square h plus q is equal to 0. In this equation, q is the recharge or discharge rate per unit volume of the aquifer. Guys, as you know, the Laplace's equation or the Poisson's equation is used under steady state condition to govern groundwater flow in a homogeneous and isotropic aquifer system. Under a transient or unsteady condition, groundwater flow equation for a confined aquifer is given here. In this equation, kx, ky, and kz are the components of hydraulic conductivity tensor. X, y, and z are the Cartesian coordinates. H is the hydraulic head. Q represents the recharge or discharge rate per unit volume of the aquifer. T is time, and SS is the specific storage of a confined aquifer. This equation relates a storage coefficient to a specific storage of a confined aquifer. In this equation, B is the thickness of confined aquifer shown here. S is a dimensionless parameter, but SAS is expressed in terms of inverse of unit length. One may ask this question: what is the difference between a storage coefficient and a specific storage? Consider in this figure, a storage coefficient is the volume of water removed from a unit area of an aquifer, I mean a confined aquifer, for a unit drop in hydraulic head. But the specific storage is the amount of water per unit volume stored or removed as a result of compressibility of aquifer material and compressibility of pore water per unit change in hydraulic head. We can use this equation to obtain the specific storage. SAS is equal to rho W multiplied by G multiplied by alpha plus N beta. In this equation, alpha is the compressibility of the aquifer materials, N is the porosity, beta represents the compressibility of the pore water, rho W is the initial density of water, G is the acceleration of gravity. It is 9.81 meter per second squared. In fluid mechanics, the compressibility of a fluid or a solid is the partial derivative of volume over the volume times the partial derivative of pressure. In this equation, beta is the compressibility, V represents the volume, and P is the pressure. This table here gives the compressibility of some materials in terms of square meter per Newton. For example, for dense sand, the compressibility varies between 2 times 10 to power of negative 8 and 1.3 times 10 to power of negative 8. For water at 25 degrees Celsius, the compressibility is 4.6 times 10 to power of negative 10, and for mercury it is 3.7 times 10 to power of negative 11. Taking this equation into account, that we described it before for a confined aquifer, and assuming that the aquifer is homogeneous and isotropic, we can write Kx is equal to Ky is equal to Kz is equal to K, which means that the hydraulic conductivity of the aquifer is independent of the direction. Then the left hand side of this equation reduces to this. A Laplacian form of this equation is given here. Del square H is equal to S over T times the partial derivative of H with respect to T. In this equation, del is an operator. S represents the storativity of aquifer. T is the aquifer transmissivity in terms of square meter per seconds. H is hydraulic head, and T denotes the time. The governing equation of groundwater flow in a confined aquifer under transient state can be solved using numerical methods such as finite element, finite difference, and finite volume methods. But in a one-dimensional case, and assuming that there is no source or sink term due to recharge or discharge, in this case this equation reduces to this one. For this equation, there is an analytical solution. It is given here. h equal to h0 times complement of error function for argument beta. Argument beta can be calculated using this expression. Here Kx is the hydraulic conductivity of aquifer, Ss is the specific storage, x represents the distance, and t is the time. By putting beta here, this equation is obtained. In this equation, h represents the head at distance x from the source and time t. h0 is the head at the source for both x and t equal to 0. Kx stands for the hydraulic conductivity in the x direction. Ss represents the specific storage of the aquifer system, and ERFC signifies the complement of error function, explaining the parameters x distance, t time, and the hydraulic properties of the aquifer system. Please note that this relationship exists between the error function and its a complement for any value of argument beta. Values for the error function and its complement for different values of the argument beta can be taken from this table. For example, for beta value equal to 0.1, the error function is 0.112463, and the complement of error function is 0.887537. The table that I explained before doesn't contain the negative values of the argument beta. In such cases, we can use these relationships to calculate the error function and its complement for negative values of argument beta. Let's consider a numerical example to examine the application of this analytical solution for head calculation. This example has three parts: part A here, and part B and part C in the next page. First, look at the part A. In an aquifer with a permeability coefficient of 1 times 10 to the power of -6 meter per second, and a storage coefficient of 1 times 10 to power of -3, and assuming an initial hydraulic head of 100 meters, calculate the amount of head at a distance of 113 meters from the initial point, and for 1 year. The thickness of the aquifer is 10 meters. Okay, we first use this equation to calculate the specific storage SS from the storage coefficient of aquifer S. So SS is equal to S over B. B is the thickness of aquifer. It is 10 meter. The result for the specific storage is 1 times 10 to a power of negative 4 meter to power of negative 1. Considering these values and putting them into the analytical equation, the result for head at distance 113 meters and for a time 1 year will be 100 times the complement of error function for a beta value of 0.1. Using this table, the complement of error function for a beta value of 0.1 is 0.887537. So the final calculated value for hydraulic head will be 88.75 meter. In part B of the example, we calculate the hydraulic gradient in the aquifer medium. The hydraulic gradient I is calculated from the difference in head values, initial head and the calculated head at distance 113 meters over the distance 113 meters. The result is 0.1. In part C, we consider a porosity of 30%. The average linear velocity can be calculated using this equation. Hydraulic conductivity times hydraulic gradient over porosity. The calculated value will be 3.6 times 10 to power of negative 7 meter per second. In order to derive the governing equation of groundwater flow in an unconfined aquifer under unsteady or transient condition, we first consider these two figures. The right figure is a confined aquifer and the left one is an unconfined aquifer. As you know, in a confined aquifer, if the hydraulic head decreases, the saturated thickness of the aquifer remains constant, but as the figure in the left side shows, in an unconfined aquifer, the saturated thickness of the aquifer changes with time. Therefore, transmissivity in an unconfined aquifer changes due to its variable thickness. So, the equation which is used for confined aquifer cannot be applied for unconfined aquifers. Considering a homogeneous and isotropic unconfined aquifer, which means the hydraulic conductivity is independent of direction, and for a two-dimensional case we can use Boussinesq equation as the governing equation for groundwater flow in unconfined aquifers. In this equation, S of y is the specific yield in unconfined aquifers. If the drawdown in the aquifer is negligibly small in comparison to the initial saturated thickness, then the variable thickness h is replaced by an average thickness b, which is assumed to be constant. So this equation reduces to this. This equation can be further summarized as these three equations. It is necessary to emphasize that this parameter is an average transmissivity in unconfined aquifers.